Okay, so here I want to talk about things that you can do with grid paper, and I want to do it at different levels. And so one of the very first things you might be doing with your students is counting things or recording data. And so first of all, grid paper like this is probably okay for high school or maybe upper middle school. If you're working with little kids, these squares are, I think, too small. It's difficult for me to work with something this size. But, here's the first thing that we could do on a grid is just show a nice way to organize something. So I don't think I want a square, I think I want a line. And so I think we could make a table. For instance, we could say age up here. And weight, height. And then we could add a few more lines like, I don't want text, I want pencil and a line, right? And you could have your students go around at the playground at Resource and just make a table like this and ask a group of friends and say, all right, how old are you? And actually, if we're doing it with kids, maybe not typing, maybe just writing. And so maybe they say, oh, my first friend was, whoa, that's not at all what I want. Escape, Control Z, not a spline. I just want a free form drawer.
Draw a line.
What? But I think draw a line is only exactly lines, right? Yeah, there is a way to draw on this thing, which I just forgot. And it's not these. Okay, that'll work. And so I can maybe make, well, I have 5. I don't know how heavy a 5-year-old is. I'm, 42 and 35 inches. And you could have your students just fill in. This is just practice writing numerals, collecting data. Once you have data at other ages, you can start doing things like analyze it. Which number is biggest? Which is smallest? What's the average? Right? That's a more complicated question. Another thing that you could do is you could have them count something. If they count something like, okay, here I have a bunch of sheep, they could just start going 1, 2, 3, 4. Maybe a better way to do the 1, 2, 3, 4 is to kind of put check marks to make sure that they don't count something again. So we could go 1 and 1. Actually, maybe let me do this. Oh, you know what? Oh yeah, I'll do it with the sheep first, do sort of a Navajo theme thing. And if I want to, let's see if I can make this a little thicker. Let's make that thicker and darker. And let's see if I can slide this so that we can do both at the same time. And so I can just make a little table here. 1, and then 2. I hope you see this. And then there's 1 hiding in the back. 3. I'll make it darker. 4. 4. 5. You've done tabulations like this before. And then 6, 7, 8, 9. I don't know if that's 1, 10. We'll pretend it is. 6, 7, 8, 9, 10. 11, 12, 13. I don't know if that's part of the same. We'll pretend not 14, 15, 16. You know. So partly by tabulating like this, you're able to count the numbers faster. We've certainly done this. When you're looking at a student, many students in a young grade wouldn't have seen this before. One of the things that you are seeing here is 5, 10, 15, and then 16. So you're seeing skip counting. Skip counting is getting you there before you start out with multiplication. In fact, here I think might be a fun way to do some skip counting with your students where we'll make a pattern in a different way and count something fun. Oh, come on. I'm having issues controlling and getting my there we go. Oops, I did not want to bring another one open. Let's do a circle. And so there's the circle. Let me copy it. And I'll come over here. And you can go in your yard and find things that they like, little toys that they might like. You might come and find something like this. And all right, so let's copy a picture and open up a paint. Okay. You could do an analogous thing on your, and paste the picture, make it big enough that we can see. And make the whole thing a little smaller. Oh, I see. Double screen trouble. I'll slide this off to the side. I'll maybe minimize the sheep. And this time, let's count puppies. Same idea. Oh, no, I want a brush. I hope this isn't too terribly tedious to watch me count, but you can do this. Doing this in the classroom on paper is probably easier than doing it with technology. But here I can do 1 puppy, 2 puppies, 3 puppies, 4 puppies. When I am doing this on the paper, this time I'm going to arrange things in a different way. Nope, Control Z. I'm going to Control copy. Hey, that might have been a smart idea. I could put the puppies over here when I'm counting. But I want to arrange these things like this, and I don't want to snap the grids. And I do want to be pasting circles. So 1, 2, 3 circles stack in a nice way. We could in fact count in groups of 3. Or a more interesting way to count, just to show an idea, is you could just have sort of a picture of the day, and let's count them. And let's do a tabulation where we count them in groups. So here I'm making a group. And what I've done is made a group of 7. And so for the puppies, I've got 1, 2, 3, 4, 5, 6, 7. There we go. And now I can keep going. Maybe keep looking for little puppies. So here's 8, 9, 10, 11, 12, 13, 14. So just over to the side on my grid, I will do a paste. And then over here, if I have a second group of 7, here's the second group of 7. Right? And so this is up to 14, and we can keep counting. It's a little tedious, but 7, 8, 9, 10, 11, 12, 13, 14, 15. That's another group of 7 plus another 1. Did we miss any puppies? Looks like maybe there's a puppy there. And so we could put in another one. So if you see what I've done, oops, nope, Control Z. This particular tabulation was exactly like doing the tally marks in groups of 5, but now I'm doing them in groups of 7. Why would I imagine doing this with, say, my 3rd graders and just giving them a fun pile of candies or a fun pile of noodles or a fun pile of rocks a couple times before class and ask them to tabulate in these patterns? A, there's pretty patterns, and you can start asking questions about what happens when you pack circles together. B, if they start making the tabulation, instead of counting this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they'll start recognizing this is 7, 14, 21. They'll start learning how to skip count by 7s. How many times do you have students that don't remember what 7 times 8 was? Imagine that you sent your students off to your next colleague where they had spent a couple months counting pretty things, grouping them in groups of 7. I bet they would start to recognize numbers like 35, 49, 56, and it might make it easier for them when they needed to learn the multiplications by 7. So what do you think? Was that something that you could use in your classroom, I'm hoping? And you have to unmute to tell me because I can't handle all of the controls at once. So let me come up to the questions before I go on. Is anybody out there? Somebody say hello. It's kind of weird when I'm in a Zoom.
Hello.
Okay.
Hi.
Is this what grade do you teach? Do you think this is something that's appropriate for your students?
I teach 3rd grade and this would be great.
Oh, awesome. I'm hoping to get some ideas. So let me show you another idea that's still on the lower end, and then I'll maybe jump and show another. I'll just show some ideas. And I can also take requests. You can say, hey, I want to use grid paper. I'm doing this grade. I've got students, this topic. Do you have things? And we can do things kind of brainstorm together. So here I went to a teaching site and I Googled Cartesian coordinates and coded picture. Okay, and so let's see, I've got lots of ordered pairs that I see here. Oh, when we do ordered pairs, that's like doing things with graphs. Seems like I have numbers that are going up to 19. What's the biggest number I'm seeing here on this thing? Let's try to get it so that I fit the page. Oh no, that's not what I wanted.
Where do you find the grid paper? Is it an app or is it in?
So I will put in the teacher workshop this particular on the web page for our workshop. This program I'm using to present is called Journal. It's free. I tend to use free things. If I want to find grid paper, I will literally type into a web browser grid paper, and there's lots of places that just have free grid paper of different sizes that you can download and print. If you don't have access to a printer and need help, let me know. I can mail you a pack of graph paper of a certain size. It's nice to have and play around. Often when we come during the summer for our summer camp, and the weekend in between, we run an in-person teacher workshop. And at that workshop, we bring up a bunch of Google supplies, and we let teachers walk through and collect the supplies, and we'll certainly have grid paper when we do that. And so that's all several different ways. So ask and we can send, shop, Google are all good ways to get grid paper. If I'm looking at this thing, I don't see any numbers bigger than 19. And so over here, if I'm going to count, maybe I don't want to go in groups of, I maybe will start with the pencil, and now maybe I'll draw a line instead of a circle, and maybe we'll change the color to this. And I'll start out by putting a dot here. That could be the origin. And then I can go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I'll go over here. And maybe I want to draw a line of a similar size going up this way. Right? And so now let's pick a different point, like let's pick black. And to get Waldo, we need 10, 4. And so I can go over 2, 4, 6, 8, 10, 2, 4, and I can put a little dot here. In fact, maybe instead of using a line, now I can go to circles and hit a Control Z and make the dot a little dot. And then it's 10, 7, 4, 5, 6, 7. Do you see how I'm plotting these points? Now, certainly when your students are in middle school, they're going to start graphing, and so they'll need to figure out how a pair of numbers like a 9 and an 8 corresponds to a dot. And an exercise like this where they're going to draw a picture where you can go over 9, and this was 7, and then up 8, and start putting dots in places, and 9, 9, gives a fun way on how to do things. What do they mean when they do this? This was certainly meant draw a line connecting those things. So they could do this on pencil and paper. They could do it electronically if you have to teach over Zoom. Maybe let's put this in a different color and I'll just connect the dots. So I go from there to there. I go from there to there. I go from here to here. Are the questions about what I meant when I made that first line? Let's do another line just to see. Then I'll show you what the answer would look like if we continued this. So if we were going to continue this, maybe I would switch to that, switch to the circle again, and I have to do 6 16s. 2, 4, 6, up 2, 4, 6, 8, 10, 12, 14, 16. So I put a circle right there. Then I need to do 7 16. Then I need to do 7 50. Then I stop. So then I can connect those with a gray line. And so we go. So this is giving your students practice plotting points in the Cartesian plane where we put the first coordinate along this axis. And what we're really doing is this is the number 1, then, 2, 3, 4, 5, 6. And so, for instance, when on the thing on the right-hand side of the screen where it said 6 16, it meant I go across the first axis, 6 different points, and then we went all the way up to 16, and that's how we plotted this point. If your students do this, what happens is, let's zoom in. There's Waldo, right? They end up drawing this little puppy and they can go, oh, it's a puppy. And you can make up your own, or you can find these things on the internet, or you can ask me. This is something that's not the usual run of the mill, oh man, do we have to do math again? That can enrich and enliven your math classes. This is what I mean over here when I say we could code a picture. Right, kind of did that one. I said make a data table, right? We talked about that one. You know, and it can be how many, how big, smallest. Encourage your students to ask questions. That's a really important part of the intellectual endeavor, is asking questions. Reward them verbally. You know, yay, this question was Michael. This question was Ervalinda's. This question was, and put it up in a prominent place in the classroom. Look at observation. Let's try something else. Let's try an exploration that uses grid paper a little bit more. Let's see if I can get a new page on this. Oh, we can do this. So for this thing, compare area and perimeter for collections of squares that share sides. So let me show you how we might do this. So if I switch to the pencil here, I could draw, and now I'll use the small squares that we have. And so, you know what? I'll actually use squares. I have those. So with one square, I can make an area of 1 and I can make a perimeter of 4. I won't write this down. If I have 2 squares, I can make an area where I can count 2 squares, and it's a little harder, but not too bad. We can count around and see what the perimeter is. 2, 2, 4 plus 2, 6. If we've got 3 squares, we could arrange our 3 squares. Actually, let me do another one like this just to put the squares in. Like this. Or we could arrange them like this. Yep. It starts getting more interesting when we get to 4 squares. If we have 4 squares, put them in a row. We could put squares like that. We could put squares like this. I'm not sure I'm going to do all of the possibilities, though maybe I did. I'm putting all around here. If I put a square here, oh no, I haven't done all. Let's do another. I can put 4 squares like this. So at this point, I want some of you to ask some questions. You have to unmute, or maybe somebody can put something in the chat. Hopefully nobody's putting anything private in the chat. Does the perimeter change when you change the shape? Oh, and we had a comment from the earlier I saw where you'd put, and oh, let's name this. So I want to illustrate what I do. So Carol, Sandy, awesome. So oh, come on. The computer's being fussy. Mm. Whoops. Try to get another one down here. So, woo, Carol, how many shapes could you get with 3 squares? Savannah. Yeah, have to get the computer to work right. So I'm missing some people in the chat. I think I warned you that I would not be good at doing the chat. In your classroom, of course, you want to pay attention and notice and recognize anybody who is responding. I like putting names up. In fact, when I'm working in a classroom, I will often use big easel paper that they have and tape it in the classroom and write kids' questions, and I'll put their names next to it. I'll write their guesses, which is very important, and I'll write their answers. And I'll name those. This is really part of the mathematical discovery. This is also giving them ownership in it. Does anybody have a guess to Carol's first question? Does the perimeter depend upon the shape? Do you think it does or does not? I get Brian says yes, Ed says yes. And so Brian, since I see you put your answer was at least the first one I saw, is that a guess that it's yes, it does? Or do you know for sure? Can you tell us why? And so is this an answer or a conjecture? The difference between an conjecture, which is a good guess or just a guess, and an answer is with an answer, you can say a reason why so that you know you're correct. So Brian, can you unmute and tell me?
Hi, good afternoon. Yeah, I think it's an answer because it is based on my observation for using the four squares.
And so is there a particular picture? Top, first one down, second one down, third one down, or which ones are you looking at?
For the original, which has four squares, so the perimeter is 10 units. Same as for the second shape and the third shape. But for the fourth shape, it has 8 units only, so the perimeter changes.
Sure. And so in fact, what I'm going to do here, just because I want to highlight this, that was very clear, very concise, and just beautiful. And it completely answered this particular question that Carol asked. And so just to illustrate what we're doing here, if I get the floating controls out of my way, come back to a text, I'm going to make a table. And the table will say, I might have to move it up, perimeter. And then maybe I'll put area, right? Just if I want to see how things behave. And over here to caption the table, P equals perimeter. And I can point out to students because it might not be obvious. Mathematicians are usually lazy, and so they might not write the whole word out, but they might just use the first letter, like they might use P for perimeter and A equals area. In fact, you see that this is really a pre-algebra skill where we can start the students using just single letters to represent words. If they see this before they're in algebra, it will help them when they're actually doing algebra. It also helps you understand when you read things, if you can follow a convention like that and go, oh, right? Oops. I should have hit a line. But, you know, if we go through here, we can see that this first thing had a perimeter of 10. In fact, if we want to continue, we can even see that the area here is 4. I think in this particular table, the area, if I'm looking on this first column, is a little bit boring because the area is always going to be 4. It was kind of interesting that the areas of, that the perimeters of the first 3 all appeared to be 10. Is that really true? I think it is, right? 3, 4, 5, 6, 7, 8, 9, 10, right? Isn't this exactly what we're getting when we do the perimeter and area of that one, of this one, of this one. And in fact, one of the things that you should recognize here is Carol's question. When she looked at these two, they had the same perimeter and same area, right? So it might lead you to guess. When you look at these three, it looks like you have the same perimeter and area. If you didn't draw this 2x2 square, you might very well have guessed that if you have 4 squares, the area is always 4 and the perimeter is always 10. But that guess would be wrong, which you recognize for sure once you get to this example, because when you get to this example, you see that the perimeter is 2, 4, 6, 8. Skip counting makes that a little easier. But it still has 4 units of area. So one pattern is if you have 4 squares, you have 4 units of area. This is really the definition of what area is. It's the number of squares. Are there questions, comments? Are you seeing a little bit how this can be used? By varying the question, you can make the problem more advanced or you can make it easy. Yeah, so Anna's saying Blockus. Blockus is a wonderful game that plays with grid shapes. In fact, you know, I've sent Blockus games to classrooms and I'm happy to do so in the future. If you don't have it and want it, I would love to, you know, ask. So often when we do math circles, we tend to start out with sort of unstructured time where they might do games or puzzles at the beginning. This is very useful. You know, what do you do with your students after they finish the test? If you have the space and they can go to another classroom or another area where they're not disturbing people working, having some puzzles and games that they can play with is wonderful. And these things can be incredibly mathematical and really build intuition. Let me do, you know, since we said Blockus, let me make something up like Blockus that would make Mateus happy. If you've seen him, let's see, save this. Let's do a file, new not document, extra pages, there, insert. I tend to, so here's a new page for us. Use this technology rarely, but we can make a collection of blocks. And so here when I'm doing the pen, this time I can make the pen tool so that it's very fine, and I can make the pen tool so that it fills in. And once I do that, I can start putting together some blocks of squares. Like I can do that, that. So Blockus is building shapes that you can by putting squares together. So yeah, somebody's never heard of Blockus before, okay? We can help you find lots of wonderful games and puzzles to share with your classrooms, and we can help provide those with you. These are things that you can ask of us. We can have a piece that looks like 4 things in a row. We could have a piece that looks like three things there with, right, I can just make the same shapes. Why might I want to have a group of shapes like this? I could make a puzzle up out of these things. For instance, a puzzle might be, let's switch up the pen a little bit, and let's make it medium, and let's make the pen not fill. And let's make a grid. And since we're playing with grids, let's make this. Oh, you know what? We can do that. I just want to make sure I get an even number of squares. Right. So I could give the problem of, can we fill this rectangle with these shapes? Now, maybe I want to have the shapes be different colors. So I could highlight this and maybe turn this one pink. Yeah, that worked. And I could highlight this one and turn this one, say, blue. And so now if we're, here we've just instantly created a puzzle, and I don't know whether this puzzle can be solved or not. But the puzzle is, can we fill this with these three shapes? And so I can just control copy and paste, and let's just stick it in there. Right? I can control copy, paste. Oh, I'm willing to bet it has a rotate feature. Oh, I see. That's rotation snapping, but not rotating. Sorry, I'm missing some of the controls that I haven't tried in a while. Well, like most things, you ask it for help and it might give it to you. Oh, that's a back, not a rotate. Okay. An easier way to do this is probably at this stage just to go back and make a new square, right? I can go to pencil and hit it at a square and change the fill. Tools. And and options. Very fine. Yeah. This program certainly does have a way to rotate shapes. I just was not remembering it. Right? But, you know, here we are. We're off and running, trying to solve the puzzle. And I don't know what the answer is. I just made it up today. I'm just playing with it. But this is very, very mathematical. At this level, the problem might even be too hard to see what the answer is. Often it's good to make the questions a little bit easier. A way I could make a question easier is start with a smaller case. So in fact, let me illustrate that here. Let's make another tile and another grid. There's a nice simple tile, and I'll change the tool format so that we don't fill. Again. And I'll make it not fill. And I'll scroll a little bit. And let's pick a different color. Escape. V. Let's save what we've been doing. Let's make our grid gray. So one of the ways that I like doing things with many students at many ages is I like to let the students be the puzzle pieces. And so many industrial kind of classroom buildings have linoleum floors, which give you an automatic tiling that you can look at and use. It's the tiles on the floor. So then you can go grab soda bottles, shoes. I actually like doing that. Shoes fit well in classroom size tiles. And so instead of using a green rectangle like I have here on the left, I could use a bunch of shoes. And I can ask the students, the first question is, can we tile this 5 by 5 square with these 1 by 2 rectangles? And so I'll ask, can we tile this 1 by 5 rectangle with, so yeah, we're getting lots of good suggestions in the chat that I'm not hearing here, like canograms is another good one. So does anybody have an answer? Can we tile the 5 by 5 square using a 1 by 2 rectangle? You can unmute and tell me your answer, or you can type it in the chat. Marge says yes. So, Marge, let's try it together, right? Because it's just playing. This is playing with math. I mean, this is sort of, as a mathematician, this is my life, right? I just get to play with things. And so, in fact, I'll make another rectangle that'll go vertically here in a second. I wonder, I might have one if I jump up to, oh, I don't. Maybe I do. Is that one vertical? It is. So do you want your tile piece like oriented up and down, or do you want it oriented left and right? You can just use U for up and L for left. Or unmute and tell me where to place these things. Is anybody out there? Oh, it's opposite for the viewer. Oh, I see. So over here, this is going to look like your right and it's my left. There is a control on Zoom where you can.
Oh, no, that is our left. When you were talking left and right, you moved it over to the right saying left. So that confused me. I'm sorry.
Oh, it's all right. So here I just put in a tile. Can you tell me where I might put another one? And do I want a vertical one or do I want a horizontal one? If we're trying to tile this thing.
Horizontal.
Horizontal. All right. So let's grab a horizontal and tell me where to put it. You see how I could be doing this in a classroom with the shoes and the students are putting their shoes off. So where do you want the horizontal one?
Does it have to connect to the one that's already there?
No, it doesn't. We're just trying to fill this square without overlaps.
Bottom right.
Bottom right. Okay. Which you notice you're really using Cartesian coordinates there. You're using the grid coordinates when you tell me, because the bottom is the y-axis and the right is kind of the x-axis. So tell me another place to go. Vertical or horizontal?
Horizontal in the top right quadrant, number 2.
Like there? Or
yes.
Over one? I don't know what you mean by number 2. Or here, is that what you meant by number 2?
Sure.
Okay. Yeah, and this is easier with an in-person activity because you can just place it. So now another vertical or horizontal placement.
So the object is to make a square.
We're trying to fill in this whole 5 by 5 square with these 1 by 2 rectangles without using any overlap. Which I think if I had edited this guy, I think it might have helped. I think I'll make another one where I edit the pen tools again, and I'll do a fill medium just so I can see the boundaries of our tiles. Oh, no. To do that, I have to switch to a pen, and I need to switch to a green, and I do. That didn't look very good. Let's even do it differently. Let's do pen. Let's make it pill. Let's do pen very thick. How about that? Yeah. And then pen very thick. That'll make the tiles look more separate. So I'm gonna be making this back to medium. And I'll be making it back to not fill. And I'll just fill in what we've done so far. Control copy. Oh, whoops. That's not what I wanted, was it? Z, because I wanted to be in this one. So we put one shoe here. We put another shoe here. We put another shoe. We could use different colors, or, you know, another shoe here. We're trying to cover this grid. Where else should we put a shoe? Marge is saying it's going to overlap now.
Yeah.
Yeah, it seems like there might be a problem. Like I've got 3 here, 3 here. You know, we can try filling in some pieces, you know, control copy. If I put this piece in over here, then over here, I would have to put this piece in like that. Then I'd have to come back to this vertical one, which I could fill in like this maybe, and there would have to be a vertical one over here. Maybe a horizontal one. You know, there's no choice in some of these places, right? The only thing that could touch this square would have to be a horizontal one. And so I'll slide a horizontal into that. Then the only thing that'll touch this square has to be a horizontal. So I'll put that in. And we're starting to get into trouble. I could put a horizontal one in here.
It's kind of like those puzzles that they had when I was a kid, that there was one piece that was always missing and you had to slide them around to try to get them.
Like the
figure them out.
That's called the 14-15 puzzle. And
Right.
the goal there is to try to arrange the pieces in a row.
Mhm.
In this particular case, our issue was to try to cover the whole 5 by 5 square with 1 by 2 rectangles. Did we succeed this time?
No.
Marge says it's going to overlap. Marge, is the fact that it's overlapping a guess and a conjecture, or is it an answer? I'll first start typing it in here with conjectures.
The only way it's covered is if it overlaps. Otherwise, you're going to have a missing piece. So it depends on if you have the
Why would you
rule
have a missing piece?
of overlapping. Can it overlap? Are you allowed to overlap it?
I think the puzzle is more interesting if you don't allow it to overlap, or is it, and let me follow my advice of naming things for people. So when I name this like this, do we see a reason why it will always miss a square?
I think there's 25 squares in the figure, and we're placing 2 by 1s. So even
2 by 1s. So
number
2,
can't fit into an
4,
odd.
6, 8, 10, even numbers, but 25 is not. Awesome. This is one of the things that we use with evens and odds. In fact, presenting even and odd is really, can you share it in an even way, which anybody who has siblings starts getting that. My sister got more than I did. It's not fair. well, can we cut it up and make it even? Oh, if there's 4 of them, we can divide between 2 of us and you get half and I get half. And so right away, this is an important step in mathematics. This is, we can recognize as remainder when you divide by 2. We can also recognize this at the same time as what's called an invariant. It's something that stays the same often. And so the number of squares that are left whenever I place a tile, there's an odd number of squares in this grid, right? There's 25. If we keep going with this, we try it again. Right? Right now there are 25 squares. If we place a tile, which we'll do just by grabbing, say, this one. Now, how many uncovered squares? How many uncovered squares are there here? I'm getting some wonderful things in the chat over here. I see that somebody indicated 26 squares with the 2 tiles would work. 2, 4, 6, 26. That's a great conjecture and idea and observation without overlapping. Carol said that there's 1 square, and I got somebody saying there's 24 squares remaining. Wait, we started with 25 squares. How many squares does the tile cover? Place a tile. Oh, I'm working accidentally the chat. Right, the tile covers 2 squares. So if I come here, place a tile, 2. So if we start with 25, I can put the comment, that's odd. A little bit of wordplay. We place a tile and cover squares. If you start with 25 and you cover up 2, what math problem are we doing? Well, 23, of course, because there's 25 squares. We subtract 2. This is subtraction that we're making our students do, which we recognize is equal to 23. That is also odd, right? If we place another tile, what happens to it? Well, when we place another tile, we're subtracting 2, which if you think about the subtracting 2, if we're playing this as a game with Skittles or M&Ms and rocks, 1 for you, 1 for me, 1 for you, 1 for me. One option of a 1 for you and a 1 for me is just taking away 2 from the set that you're sharing from. And if you're starting with an odd number of things, as you share and you divvy things out equally, there will be an odd number each time you go through. You're never changing that number. The fact that it's odd is what we call an invariant. Meaning it does not change. And this is, in fact, a reason why you can't cover a 5 by 5 with 1 by 2s and 2 by 1s, because you have an odd number. You subtract 2, you subtract 2, you keep subtracting 2, you always have an odd number. You will never get to 0 because 0 is an even number. Does this make sense? There's actually another puzzle and problem here, and that is that we could cover up 1 square. So in this particular case, let's go back to the tools and the pen, and we'll make it very thick, and we will make it a fill. And I will make a square over here on the side. And I'll do it in a different color, maybe this purple color. And I'll go to select. So you see that in this thing, if I had placed 1 purple square here, I would have started with 25, I would have subtracted 1, and now I would have 24. If I have 24, am I going to be able to cover it with the 2 by 1 tiles? What do we think? So Miss Good says yes. Okay, let's try it. So here I'm actually going to save this. Rosemarie said yes. Awesome. We're having a question and we're having our answers, right? I need a new page. So let's see. I think that might have been journal. New page after. And control paste. Text. This is a 2-person conjecture. Is it Good and Jones was good with an E on the end of it? Yeah.
Yes.
So this is, oops. If you read math papers, you will see in the literature, people will talk about the so-and-so and so-and-so conjecture, or the such and such conjecture. The Good-Jones conjecture is if you cover just 1 square of 5 by 5, then you can cover the rest with 1 by 2s and 2 by 1s. Actually getting your students to write their guesses and their questions and the answers, getting them to enunciate it. It's all good practice of speaking and presenting. And so now I'm going to scroll up and steal a copy of this guy. And I will put it here. And I will steal a copy of this guy. This is our vertical placement. I'll just put it over to the side. And we'll play with filling this in with our shoes and see if we can do it. And I'll steal a copy of this guy. So Let's try. Where would you like me to place a tile, and do you want it to be horizontal or vertical?
Horizontal above the pink square, please.
All righty.
I agree.
Now where? Horizontal, vertical?
Vertical.
Vertical. It was sort of forced that we did a horizontal because it couldn't hit that square with a vertical. Sure. So now where?
Below the pink square.
Okay.
Yeah.
Now it's a little tricky here because this is one possibility. It's not forced like the one above it. So we could make a note that we're trying this configuration. In fact, I'm going to record the fact that we're trying right here. Yeah. And we might be able to branch off without sticking one here. So another thing that I'll put is at this point, maybe I want to take that and get rid of it. Whoops. I can fill these back in. Like that. So we could have tried a different placement for this thing. But in fact, if you look at this square just beneath the pink one, there's only two possibilities. That square is either touched by a vertical or it's touched by a horizontal. If we want to include those possibilities,
Well, and you could also do horizontal branching out from the pink.
right. But in some cases, there's going to be something forced. Do you agree that we either have to have the one on the left or the one on the right? There's no other possibility. This square beneath the pink has to be hit by a vertical or a horizontal, right? And so now, are there other squares forced? I think on the one on the left, there's a forced square. What would have to be forced? What has to go in where my plus sign is?
Horizontal.
It has to be horizontal. There is no choice.
But on the other one, you could do 2 vertical from the one that branched off from the pink.
Here I have a choice. I could do 2 vertical or I could do 2 horizontal, though there is something that's forced on this one. Let's look at the one on the right. Do you see a forced move that's here?
Yes.
What's forced? And somebody said yes, that there's one forced. Where is a forced?
Horizontal to the right of the pink.
Next to the pink. I can't put vertical going up from here or going down from here. So that would have to be a horizontal. Once you get to a point where the puzzle's forced, is there another one that's forced? Then it really starts filling in. So look at this square. What direction would you have to be if you were in the square where the plus is now?
Horizontal.
Horizontal.
So now what does this square have to be?
Vertical.
There's no choice, right? And so we can just immediately fill in what's going to happen here.
vertical, vertical.
And another vertical is forced, just like laying bricks.
Another vertical on the side, or in.
There's another vertical spot. We see that all of these have to be verticals when we have that. And in fact, I see another vertical. Huh. So am I ever going to get this square?
No.
So that means that if I place the first tile in the corner going up this side next to this pink one, if I have the pink one, it has to come across like this, then we have to go with the range where we go down. We can't go to the right because it was just forced to give us this thing. And so then it has to be this, and this has to be fixed. So in fact, I'll copy this part here, because now I think we might have another choice. So now I don't see any others that are forced. So I could take a look at this square next to the pink one, and I can type in the word or here, just like we did before. Because there's two choices. The one next to the pink can either be, what are our possibilities?
Vertical.
Sure. So one possibility is it could be vertical.
Horizontal.
And the other possibility is it could be horizontal. That's all there is, right? And in fact, as soon as I do those, things start getting forced. So let's do the one on the left. If I've done the one on the left, what do we see about this square where the plus sign is?
Horizontal. Horizontal.
Mm-hmm. And then is there another forced one? Once we start getting into sort of this brick region, you start getting lots of forced placements.
Yeah.
And then it looks like maybe we're doing another vertical is forced there.
The top one as well.
Right, you see that I've got this one square, it has to have a vertical, is the only one that fits. Then that locks in the ones on the side. That locks in this one. And look, there's two squares that we can't reach. So this is not possible, which means putting a vertical next to the pink square after we put a vertical underneath it will not work. What about if we do a horizontal? Well, I think there's some forced positions. If I have a horizontal, do you see one that's going to be forced?
Yes.
Above it, right? Right there. There's nothing else we can do. That has to go in that direction. But now there's something else that's forced, right? You see, just when you have those lonely squares, things are forced.
At the end.
And then we just start filling in when we've got those single holes. There's only one way things can fit. And when we fill in those things where there's only one way that things can fit, pretty soon it gets rather locked up.
the bottom.
There's no choice. If I'm looking at this square here, the only one that would go in that square would be a horizontal one. And as soon as I put that horizontal square in, I'm doomed. This single square I can't get. So what do we think about this, the Good-Jones conjecture? Is it true or false?
Go back up, down.
Go back down, okay.
It depends where you put the pink ones.
So when we said the Good-Jones conjecture like this, it was, if somebody else covers a square, if you don't have a choice of where it's covered, then it might not be possible to do it. And so as a mathematician, when I do this, I mean that, somehow it's, if the first person picks the square, can the second person always fill it in? And the answer we see from here is no. No. There's something more than just the answer that I want to put in, and that is I want to put in this is why. You see the argument that I went down here? Here I'm giving absolute argument of saying where it's there. And so partly there's a language issue. Carol's going, but wait, that's not what I meant. I meant that if I can place the square, I will pick the pink square here on the edge. In fact, there's kind of an interesting question of let's find the good squares versus the bad squares. This position here, maybe I will recolor this square. And let's see if I have something yellow. Yeah, I've got something yellow like that. And so our yellows can be our happy squares and our green are our bricks. And then the pink are going to be the unhappy squares. Let's see if we can find out happy and unhappy squares and analyze this. And we'll see a pattern that might lead to a better argument of this. So actually, I'll just do this. So this square here is a happy yellow square. Do you see what I mean by happy yellow? It means that if I color this one square in, following Jones good, there's going to be an even number left. And so we think we can fill that in, which in fact we could. Now, when I'm putting these squares in this diagram, what I mean is if we place just one of the single colored squares, what happens? And so let's think if I knocked out this square on the bottom, could I, and did not cover this one. In other words, if I took this and I moved it over to here, and I see that I make a goof when I do that. So control copy, control paste, and put that square back. Could I fill the rest of this 5x5 grid with green bricks? I see a yes that was typed here. I don't know if it was typed after my question. Then yes, right? And what's the reason why? And so it's not just the answer. I encourage you to go that one step further and have your students say why. How is there a way that, yes, we could just fill this in with green bricks, but do you see a shortcut how I could take the picture here to make the picture here? What do I do to the picture on the left to get it to the picture on the right. Yes, if we turn it clockwise by 90 degrees, a 90-degree clockwise turn would move this square to here, which means that we can fill this thing not only if I put my yellow square here, but also here on the bottom. You see that then we could turn it again, and we could put a yellow square here or a yellow square here. And so certainly yellow squares in the middle of the edges are good squares that we could put and cancel out and make the rest with bricks. So I'll mark those like that. Maybe you're going to see a pattern develop here. Actually, we know a bad square, right? Let's see if we can do the same argument. Do you see that this pink square would not work? That's the one that we just did. That's the one that we did down here. When you put a pink square, no matter what you do, there's only a couple real choices. There's only, does this one go vertical or horizontal? If it goes vertical, does the one next to this go vertical or horizontal? So there's really only 4 things to try. So we're getting any middle, this is any middle square on the edge, or I don't know exactly what the word middle means. What about put it in the center? Yeah, great question. So let's do that. And we should also think if there's some easy answers that we can get by putting a pink that looks there. I claim that there are some easies. Before I try putting it in the center, can we see other places where, what if we put the pink square here? How does putting a pink square here relate to putting a pink square here? So if I put it up on the top near the corner, could you see a way of translating the argument that we have here to the argument that we have putting the pink square where the plus is? You have even squares on the top and to the right of the pink. Yeah, somehow there's something. So there's, what we did to get these yellows is we rotated. Rotating is a symmetry. Let me draw a line here. Think about reflecting this in this line. If I reflect this picture in this line, the pink square here would move to the pink square here. And so if I could cover it when there was a pink square in this upper left, then I would be able to cover it when the pink square was here, because I would take the one where it was here and I would just flip it across this line of symmetry. So what that tells us is that it's not possible to fill in dominoes when it's there. In fact, using the same line of symmetry argument, we could reflect in the line that runs through the middle, like this. And in doing that, see that we would also put a pink square here would not be possible, and a pink square here would not be possible. And then we could even rotate it and start, in fact, if we rotate it, we could put these two to here. We could put those two to here. We could put those two to here. So all of those are impossible tiling placements. So when we did the one case, in fact, by using symmetry, we see that we really did 8 cases. That's nice and lazy for us. And we start getting something that's fun, right? I mean, at least visually pretty, I hope. All of those are impossible squares. Now let's come and ask the question about the grid in the center. I think this one is about the closest to the center. Since I don't know the answer to the center, I don't know if I should color it green or purple. I'll tell you what, I'll make up a different color and drop it in. The way I'll do that is let's make it blue. And so let's try to tile this to see if this is a good square or a bad square. By symmetry, I could reflect in this purple line like that, using that same symmetry argument again, so that if I could get a solution with the tile placed like this, then I could get the solution with the tile placed like this. So there's really no difference between vertical and horizontal. We still might have a choice to figure out here. I think there's now maybe two possibilities for where does the next tile go. So if I'm looking at this square where the plus is, would that be horizontal or vertical?
Either.
Either. And so in fact, I can make an or. We could also just make our best guess. If we find an answer, we're done. So tell me, do you want to make this square happening here vertical or horizontal?
Horizontal.
Horizontal. All right. So let's copy a horizontal one. Now that's going to force things. Suddenly this square where my plus is has to be horizontal.
Mm-hmm.
Seems like I have another choice. What about this one?
Well, if you go vertical with that, then you have to go vertical with the next one over. Or you could go horizontal and horizontal.
So now what? You might even see a way where you can kind of fill it in fast.
Either horizontal or vertical.
So which one do you want? Pick one for where it's plus.
Could do horizontal.
Vertical.
Or vertical, either one.
Okay.
They have to be vertical.
Well, does it have to be? Since you said the word half.
Yeah. I looked at
actually just to be perverse and mean that. Does it really have to be, Mrs.? Let's stick in, if I stick in a horizontal one there, I don't see anything forced. In fact, I might even see something like, here's a lemma. When you're solving a problem, if you've solved a big chunk, you can just copy and paste. You see how I've got this 1, 2, 3, 4, 5 bricks? I could place those 5 bricks somewhere else in the diagram, and that's saving me a step. That's a subroutine if you're writing a computer program. It's a lemma if you're doing mathematics. So you know, that allows me to fill things in faster. And then in fact, oh, it doesn't seem like it had to be vertical. It seems like it could have been horizontal. It doesn't ask if it could have been vertical there. I think it probably could have. I think this middle square is going to be a pretty good square, and there'll be maybe several ways of answering the puzzle when you stick it in the middle. So is this blue square yellow or purple? So is this a good square or a bad square? So is it yellow good or purple not good? It's good, it's yellow, sure. So I can take this, copy, and paste. We just have a few more options left to go. You have more options when in the center middle square is covered, yeah. And so you're not even locked in. It's not a unique option here. So we need to see what happens if we put a square in a corner. We need to see what happens if you put it here. What happens if you put it here? Do you have a conjecture? Is the corner of the big square going to be yellow or purple?
Yellow.
Yellow. And do we have an easy way to do that? An easy way to do that might be able to take one that's filled in and just slide it around a little bit. And so, in fact, one that's actually kind of close is maybe this first one. Oh, I wish I had had a couple vertical placements here. But you know what? I can change this just by changing 3 tiles, I think. Let's look at this, right? Because I've already filled in a lot. New page after. And let's slide that over and off. I won't put in the grid squares because we kind of know they're there. I'll slide these guys off to the side as well. And I'll put this one in the lower corner. And so now what kind of squares do I need to fill in here? There's only one choice, and there's only one choice here. And luckily I happen to have pieces that look like that. One piece can go here. This is actually a really important subtle thing, is I've found one result, namely when I was putting it on the side, and then I was able to change it and get a different result, namely when I put it on the corner, so I didn't have to repeat all of this work. And that told us that all of the corners are yellow. So in fact, we now only have 2 other types of squares, the type of square where the plus is now, and the type of square where the plus would be over here. Does this make sense? Because if I know the answer to this square, the answer would be the same for this, this, by the clockwise rotation. And so to try to figure out these squares, I could just try to move this so that this yellow went down to here, which would sort of open up. Let's try that. Or I have done it with in the corner and I can try to move it to the piece. So we can scroll that down and just move a little bit. Oh, don't scroll so fast. So we don't want the yellow there. We want to put the yellow here. So I need to get rid of that green block. And put the yellow in over here. Oh, but now can we complete the puzzle? So what do we need to do?
Have
How
it
do we-
go horizontally.
Sure. So are these squares, is this square yellow or pink where the plus is? We just did this one, right? When we put it just sort of like this at the diagonal, we were able to fill that in. Which means that by the rotation argument, we could fill it in when it was here. Or we could fill it in when it was here by rotating again. Or we could fill it in when it was here. A pattern is developing, yes? Maybe this pattern helps you. What color do you think this square should be?
Purple.
Yeah, and so to try that, we're just going to make a copy of our square and we'll put a purple in there and see what has to happen. Here's a square with a small number. What else to the side? Reassemble my square. Go grab a purple square from up above. Like maybe that one. And we were thinking about putting a purple square here. No, it was here. In fact, that is going to force what direction the rectangle that goes to this square has to be. This can't be horizontal, it has to be vertical. It looks like there's two choices, like it could go up or it could go down, but really if I can do it with it going down by reflecting in the line here, it would have to go, I'd have to be able to do it when it went up, which means that using the reflection argument in this line, we can say that the rectangle has to go like that. after reflecting, I can make it like that, but that now forces another rectangle position. You see here, there's just one square. When you have the lonely squares, things are forced. If things are forced, it goes fast. Then there's another lonely square, so another forced placement. And then another lonely square, so now we're laying bricks. Another lonely square, so forced placement. Another lonely square, another forced placement, and so it goes. So far, there's been absolutely no choice if we take into account the symmetry. All of these moves are forced on us. Looking at this square, it's forced. We have to lay the bricks. It's the only one that fits. And as soon as we get to there, we see that there's nothing we could do with this square. It can't be horizontal. It can't be vertical. So that means it's not possible, which means that as we conjectured, these guys are all purple. I have to paste it and move it in. I probably should have given you guys a break in the middle of this. I'm sometimes a little absent-minded and a little oblivious. I will certainly give applause here. Questions, comments, thoughts?